Make a start. Congratulations on making it in on a snowy morning at 9 o'clock. Well, this morning, of course, we're going for the big one. And in fact, we've done all the hard work, really. And I think the final derivation of the unification theory is not so incredibly difficult once we've got to the stage that we've got. So I mentioned this the last time. We've got the full set of Maxwell equations. We're now going to go over to what are called Maxwell's equations in free space. So the idea is if you are far away from any charges or currents, and of course all the laws of early laws of electricity and magnetism were discovered close to the sources of charges and currents. So in other words, we're going to make the approximation that rho is naught and J is naught. So we're going to move away from the charges and currents. Then we get Maxwell's equations in free space. And this Maxwell's equations in free space is the name given to the four equations that I'll put up now. So we've got del dot E is equal to 0. So this is a long way away from all of the charges. So the divergence of the electric field has gone to 0. Faraday's law is still, of course, true, always true. We've now got the dynamic electric field in terms of the magnetic field. We've got, as always, del dot B is equal to naught. That's always true. And now again, we're making the approximation to the Ampere-Maxwell law that we can throw away the mu naught J term and just keep the dynamic term mu naught epsilon naught dE by dt. And of course we've got four equations and we'll use all four, but the two that we're most interested in are combining these equations. So these are the ones I'm going to number up today. So we first of all started, with electrostatics, then magnetostatics, then we derived, or if you like, abstracted Faraday's law from the dynamic magnetic field, and then we saw that the whole of the last lecture was about consequences of this term in combination with the mu naught J, and we're now moving away from the sources and we've just got the dynamic effects remaining. And if you like, equations 11.1 and 11.2 are basically a pair of simultaneous equations, and we're going to eliminate the magnetic field by taking the curl of equation 11.1. So we take the curl, of course, of both sides of equation 11.1. So we've therefore got that the curl of E, taking the curl of the left side, is equal to, and again I've mentioned this a few times, that the curl of dB by dt, we're taking the curl of this, but I can always change the order of space and time differentiation. So the curl of dB by dt is d by dt of the curl of B, and we have here this straightforward equation. But that's the point of the elimination, is that we know from this equation what the curl of B is. It's mu naught epsilon naught dE by dt. So that we've got, well, let's make this 11.3 so that we can go through gradually all the steps. This is minus d by dt of mu naught epsilon naught dE by dt. And clearly now we've got an equation which is purely an equation for the electric field. And therefore, i.e., that the curl of E is equal to, well, of course, we can take these two fundamental scalar quantities out the front and write this as minus mu naught epsilon naught. And similarly, d by dt of dE by dt is just d2E by dt squared. So let's let's take it gradually. Let's number this one up as equation 11.4. So this is why, I stressed, we did this when we were studying the vector potential in lecture 5. We used the expression for the curl of the curl, and that was one, because it's such an important equation in the derivation. I even sent that out, in an email, and we've got all of those components written out. Give us very simply. Oh, we've got a whiteboard underneath here. I've named V45. We won't have any, pens that work on it, but you never know your luck. So we'll try one of these. Just to emphasise that just by writing out the components, there's no magic to this. We saw that if you just write out all the components, we can prove, and we say if you refer back to lecture 5, we already use this. And it's true for any vector field, so it's certainly true for the electric field, that the curl of the curl is equal to the gradient of the divergence minus the Laplacian applied to the field. And again, just to stress, this is a vector equation. The curl of E is a vector, so its curl is a vector. This is the scalar quantity. This is the gradient of a scalar, so it's a vector. This is a scalar operator on a vector. This is a vector. So this is a straightforward, pure vector calculus relationship that's true for any vector. But now you see, this is the point of taking our free space approximation. In free space, del dot E is equal to 0. If we're far away from any sources of charge, then this term is 0. So this is not generally true, but del dot E is naught in free space. This is an important part of the argument. We've got to be away from the sources for this to be true. So in free space, we've got that the curl of E, and actually this is not so different from what we did when we were looking at the vector potential. Remember there we chose del dot A to be naught as so-called as our choice of gauge for solving the problem. So we've got a similar relationship, but now for the electric field is just equal to minus del squared E. And again, there's absolutely no physics in this at all. This is mathematically true. We're putting some physics in here. This is our free space approximation. And given that approximation, we can replace the curl of the curl on the left-hand side of equation 11.4 with minus the Laplacian applied to the same field. So, so equation, let's move this up a bit, equation 11.4 becomes, well, again, I'm just going to take out the minus signs. Of course, I've got a minus del squared E on this side of the equation is equal to a minus mu naught epsilon naught dE by dt squared. So, of course, I get rid of the minus signs and just write this equation as del squared applied to the electric field is equal to mu naught epsilon naught d2E by dt squared. And this is, if you like, our vital equation. Now Maxwell, and there he is looking down, he's a bit distorted today because I needed the blackboard, so he's been projected into the corner and his nose has got kind of a bit stretched out. He was so good at maths, he immediately recognised this as a vector wave equation and went straight to the answer that he could identify mu naught epsilon naught with 1 over the speed of transmission of the electric waves. But because, so far, I think with Phil last year, you only did scalar wave equations, I'm going to reduce this to an effective scalar wave equation to make it a bit more convincing. So this is an equation that, as I mentioned this many times in the course, sometimes when we use the compact kind of notation, it actually obscures things. Let's write it out explicitly. So I'm just saying the same thing, but I'm going to write d2 by dx squared plus d2 by dy squared plus d2 by dz squared. This is just writing this scalar operator out explicitly, applied to the electric field, is equal to mu naught epsilon naught d2e by dt squared. And so again, you know, one of the things I've stressed throughout the course is that, again, this itself is still, although I've expanded out this scalar operator, written it explicitly in its Cartesian form, this is three equations. If I apply this operator to Ex, it's equal to mu naught epsilon naught d2 by dt squared Ex. If I apply it to Ey, I get this operator applied to Ey is equal to d2 by dt squared of Ey, and so on. So that this is three equations. Now you'll see why I make this choice later in the lecture. I'm going to particularly choose the y component. So this is three equations compacted into one, and let us consider one of the components. And this will fit in with an alternative derivation that I'm going to give in the second half. Let us consider one of the components, and let's choose, for example, Ey. And then we get that the d2 by dx squared plus d2 by dy squared plus d2 by dz squared, Laplacian operator applied to Ey, is equal to d2 by dt squared applied to Ey. So now again, this is, of course, a slightly different looking proposition to the wave equations that you've studied so far. So again, I'm going to consider that the Ey varies in x direction only. And in the demonstration that I'm going to do, I'm going to make if you like, the plane of the board, the YZ plane, and I'm going to show that the whole of the, you know, like illustrate what these equations mean with the x direction going towards u, just straight down. Yes, Camilla. Oh, thank you very much. Maxwell frowns down at me as you see, he's looking a bit distorted. Thank you. Yes, it's mu naught epsilon naught d2Ey by dt squared. Thank you. The old disappearing mu naught epsilon naught trick. So if the displacement, again, this is, we can consider more than one case, but if the displacement varies in one dimension only, e.g. the x direction, so I'm going to consider what are called plane waves, and we'll be using these plane waves a lot when we do optics, because it makes things easier than, you know, in the maths than doing spherical waves. Well, in that case, if things aren't varying in the YZ plane, if everything's constant in the YZ plane and all the variation is just in the x direction, this simply becomes d2 by dx squared of Ey is equal to mu naught epsilon naught d2 by dt squared of Ey. So, and this is let's make this equation 11.6. We have now got something that I hope you recognise, and I mentioned that, you know, I did a little introduction about what is a wave equation, and this precisely is a wave equation. I mean, if you like, just to make it completely identical with what I studied last time, we could call the y component of the electric field psi. Just give it a name. Oh, I'm going to call the x component of the electric field psi, or so if you like, using psi as a notation for Ey, we've got an equation of the form d2 psi by dx squared is 1 over, excuse me, is mu naught epsilon naught d2 psi by dt squared. And this is something again that I sent out to emphasize that, and this is very, very similar to what you did when you calculated with Phil last year, transverse waves on a string. This is the physics, gives you this equation, but this is a wave equation of the form, again, save board space by halving it, of the form d2 psi by dx squared is equal to 1 over c squared, 1 over the velocity of the wave squared, times d2 psi by dt squared. So this is, like, as I say, this amazing moment in physics that when Maxwell solved these equations in free space, he got an equation which is clearly a wave equation, so he could identify this constant, the 1 over c squared, where c is the velocity of propagation of he called them the transverse vibrations, with mu naught epsilon naught. So identifying these two equations, so let's make this, if you like, equation 11(7). So thus Maxwell predicted the existence, and I think he was as kind of surprised by the answer as anybody at first, of electromagnetic waves propagating, isn't it, with a velocity c given by 1 over c squared is mu naught epsilon naught, or c is equal to 1 over the square root of mu naught epsilon naught. So let's make that equation 11(8). And so just to go back, usual problem in here, back to this board, and use the space here. So, of course, he wasn't working at the time in SI units, but obviously we now use SI units. You've got mu naught is equal, I'm only going to do it to 3 sig figs. They're known to more sig figs, but it's just the point that I want to make, usually written in henries per metre. Epsilon naught, can you see this over the lectern here? Yeah. Epsilon naught is 8.85 times 10 to the minus 12 farads per metre. And so the velocity of these electromagnetic waves in SI units is 3.00 times 10 to the 8 metres per second. So that was this truly amazing calculation. We've been building up to it throughout the course so far, and by abstracting these differential equations, again he was using miles per second, by performing this calculation and identifying that they produced a wave equation for the electric field, we get this identification of the 1 over c squared with mu naught epsilon naught, and then 3 subjects which had thought to have been quite distinct, electricity, magnetism and optics, are now unified into a single theory. And this, again, you sometimes see this result popped into textbooks, but I think it's very satisfying to see exactly where it came from. And I think if you've followed the course all the way through, you'll see that this is quite inevitable. One of the things that puzzles people and makes them think electromagnetic waves are somewhat different to others is that almost every time you do a calculation of waves, you end up with a velocity which is the square root of something over the square root of something else. And for example, yeah, if you flick a string, and in that case, this, if you're flicking a string, this psi would represent the y. Let's say you're flicking a string which is, again, this is sort of an analogy with what I'm going to do next time, is that in that case, you would just have, well, if there's the y-axis and there's the x-axis, and I kind of give a string a flick and the wave sets off along there, this would just be d2y by dt squared on both sides. And this would be, from Newton's laws of motion, this would be equal to mu over the tension in the string. And then you'd say, oh, well, 1 over c squared is the mass per unit length over the tension in the string, and so c is root t over mu. The only reason that it looks different, and I mean, again, you didn't probably do this one last year, the speed of longitudinal waves of a rod. So again, if you whack one end of a great big lump of material of density rho, and Young's modulus related to the strength of the material comes out as something over something else. The only reason it looks weird for electromagnetic waves is from the very start we got the constant, which of course corresponds, we saw, it's written in this odd way of a 1 over epsilon naught, and that's because at the very beginning, the force between two charges, where everything started off with Coulomb, over 4 pi epsilon naught r squared times the unit vector between the charges, the epsilon naught came out in the denominator. And it would be, we're never going to rewrite that. Every book in physics has been written where this, like in Newton's law, if we replace these with masses, it's gm1m2 over r squared. But in electricity, the original people gave the constant in this 1 over 4 pi epsilon naught form. So if it had been defined in this way, which would have been more natural with the epsilon naught in the numerator, the speed of light would have come out in those units as epsilon naught over mu naught, and it would have looked much more like all of the mechanical waves. But the way the constant got written means that it comes out in this way. And certainly when you put in your 1 over 4 pi epsilon naught corresponding to the force law of Coulomb, and the mu naught from the law of Ampere, you get this result for the propagation of the waves. So that gives us, this very amazing moment in physics. And because it is such a big calculation, I'm going to do it in a completely different way to show this result in a kind of slightly more intuitive way. And also there's a big point to this, because these are three-dimensional. This isn't just, we haven't just flicked a string here, we've also got waves of magnetism going out as well. And I think you'll find it pretty easy to imagine. I could have done the identical calculation by taking the curl of this equation, taking the curl of B, and then I would have had d by dt of the curl of B, and I would have substituted, of the curl of E, and then I'd have substituted in for the curl here, and I would have got a three-dimensional wave equation for the magnetic field as well. So the three-dimensional equation for the magnetic field would also have given us the same type of equation, and we'd have magnetic effects propagating out at velocity c as well. But they have a very specific geometric arrangement to each other. And I'm coming back to Maxwell's equations in free space next time, so I'm going to go straight to the answer, which, as usual, I've cribbed from Feynman. Now, the idea of, it's the usual problem in here. I've run out of board space. I'll make some board notes on this in lecture 12. And lecture 12 is called Maxwell's equations in free space. It's basically a continuation of this one. So I'd like you, it's probably best just to try and follow the calculation now, and I'll make some board notes as we go along. The reason that I chose the y direction as my example is that this is exactly what's happening here. I've got the y direction as the y direction here, I've got the z direction here, and this is what I say, I'm going to make the plane of the blackboard the YZ plane. Now the idea is that I shake a charge. So imagine that behind this there is an infinite, you know, it's phys, so it's an infinite flat plane of negative charge is the whiteboard. The whiteboard is an infinite flat plane of negative charge, which you can tell because I'm just going to write negative on it. Look at that, there we go. That's a pretty convincing infinite plane. And this is an infinite plane of positive charge. Now, of course, they're physicist planes, so they're infinitesimally close together. So there's no electrical effects anywhere in the room because they're positives and negatives cancel each other out. There's absolutely no electrical effect here whatsoever. Now, what would happen, as I can do, if I shove this board upwards, give it a sudden shove upwards? Well, I've developed a current, haven't I? There's no electrical effects. There's still an infinite negative and positive plane cancelling, but now I've produced a positive current, positive the front board, and so I get a current flowing up the board. Now, by Ampere's law, it is difficult to solve things close to the sheet, but so this is more an intuitive proof. Don't take everything here completely literally. This is slightly more intuitive. So let's consider one part of this infinite plane, a little sort of strip of current going here. Well, we know from Ampere's law that if the current goes up, right-hand screw rule, there'll be a magnetic field that goes round here to the left. Yeah, it'll curve round in this sense. So the magnetic field will come out here and go round. So it'll go round to the left, yeah? But then the next adjacent bit of this infinite sheet will also produce a current that does the same. And this bit of the infinite sheet will produce a magnetic field going like this. So what will happen, that coming out towards you, this will give, and we're going to come to this in optics, it's called Huygens construction. You may have seen it, is that each one of these will produce a magnetic field doing this. When you add them all up, it just produces a magnetic field going in this way. So we know if we had an individual wire, it will produce a circulation where going out front in the remember the positive x direction is going down the middle, we've got a magnetic field going to the left. So if I shake this whole sheet upwards, if I give it a kick upwards, I get a magnetic field which goes in the positive positive yes, it's here the z direction, yeah. So we've got the z direction this way, and now again it's possibly a bit harder just from this intuitive argument to see why the electric field corresponding to this is in the negative y direction. We'll assume, and it's a good, we can prove it, and it's proved from first principles in Feynman. But I don't want to write out all the components here. I just like to get the overall geometry. So the x direction is going towards you, and as I see it, the magnetic field is going to my left. It's going across in the positive z direction. Now again, we could use a bit of intuition and say, well, we know, and because you've got curls involved, and they're basically like cross products, that's why the electric field is at right angles to both the magnetic field and the direction of propagation. So the direction of propagation of the wave is along x. You've got this wave of magnetism and electricity where the electric field is pointing down this way. And so what's happening here is that a wave is just heading out from the board. It's electricity, so the wave's heading that way, the magnetic field is oscillating this way, and the electric field's oscillating this way, all at right angles to each other. Now, if we just assume that the velocity of propagation is just not infinite, well, I'm the first one in the lecture theatre to know about this wave. At the back, you know, Connor there, Hugo, you don't know that I've shaken the board yet. You know, the wave hasn't arrived at you. If it's got a finite propagation, when I kick the board upwards, I get this wave, plane wave, magnetism to the left, electric field this way, heading out, and then the front row gets it, and then the next row, and the next row, and the next row. Everybody gets it successively. And I don't have to make any statement about it other than that it's finite. Only if it was propagating infinitely quickly would people at the back of the lecture theatre know that I've shaken this board up at the same time as me and people at the front. So if it's got any finite velocity v, and we're not calling it c yet, we're just saying it's got a finite velocity v, well, it propagates out in a way shown in the next slide. And then first of all, what I'm going to do is look at two views. First of all, I'm going to imagine, and I've said before, you do need a bit of 3D imagination to do, there's my, oh, there we go. I'm going to look back along the z-axis, so I'm going to look at things that way. And when I look at things that way, let's call it the side view of this situation, I see the magnetic field lines all pointing along my direction of vision. I see the electric field lines pointing downwards, and then the direction of propagation heading out towards you. So when I look, so this is the current sheet, which obviously I put at the origin. This is the actual sheet. Let's forget about what happens at the moment behind the sheet. We'll come to that on Friday. The magnetic field lines, the B field lines now are, I'm seeing the feather of the arrow. They're going into the plane of the view graph. The E field lines, remember, were pointing in negative y direction. So the E field lines are downwards and the wave is heading in this direction. Now, provided the velocity is not infinite, then I've got at some point, if the velocity isn't infinite, the wave has reached some quite definite point after a time t. It's reached this finite point here, vt, this distance, because it's been travelling for t seconds at this velocity. Well, now, of course, the wavefront is always moving, and a time delta t later, it's moved this little extra distance over to v delta t. So, and now this is, it's just like, again, if you're really, sharp, you'll have seen that this is incredibly similar to the problem that we did with Faraday's law. We've got a magnetic field out of the plane. We've got, in that case, it was a real physical circuit. Yeah, it was a crossbar moving, cutting the magnetic field lines. But now, and we got this result, that the EMF induced around the loop was the constant field strength times the width of the crossbar times the velocity with which we move the crossbar. We're using the same argument now in a different physical circumstance. We throw this Stokes loop gamma 2 around the wavefront. And again, we've used this kind of rectangular Stokes loop when we analysed the solenoid. Now, particularly here, I mean, that is, that's the clean mathematical derivation. Yeah, that is like the pure mathematicians totally happy already with what's happened. But now we can use Faraday's law again, because as we go round this loop, we've cleverly put this loop around the wavefront so that in this part, when we go round this loop, well, as I go along, and again, I'm looking now at this part here, this side, as I'm going around the loop, well, here, the electric field, remember, is in the negative y direction in this geometry. So my E dot ds is 0 all along this part, because this side of the loop, as I take my displacement round here, it's perpendicular to EY. So obviously this scalar product is 0. So I get nothing from this leg. When I go round this leg here, I do get something, because now I've got the E field lines anti-parallel to ds. ds is going up here. The E field is in negative y, so I get from this side of the Stokes loop, I get minus E times L, where L is this width. And then using the argument again, if I come round here, again, we've got a right angle, and if I go round, complete my Stokes loop, and I go round a complete circuit, this closed circuit, well, out here there's no field. The wave hasn't reached that point yet. Therefore, the left-hand side of Faraday's law just becomes, well, it's minus EL, but I've cancelled off the minus sign here, so I just get EL. But now, again, same argument as we use here, the magnetic field lines are coming out of the plane, so given that we're cutting across them, now the difference now, it's the same maths, is that the magnetic field is changing because a wave of magnetism is sweeping through this loop. A wave of magnetism is sweeping through this loop. But of course, I get the same result. The field is perpendicular, so B dot N is just the magnitude of B, which as usual we abbreviate to B. The area of the loop is of course this length times this distance here, the x, if you like, displacement, and when I take d by dt of that, this isn't changing, but I've got a dx by dt, so I get the velocity term. So if I throw a Stokes loop round the wavefront looking, this sense at the wave, where that's the x direction, I get that of course the L's cancel out, and I get that E is equal to BV. And this, incidentally, is, so I'll make board notes on it. This is true of any, although this is a simple example, this is true of any electromagnetic wave. The ratio of the electric field vector to the magnetic field vector is equal to the speed of light. And often, we'll use an approximation when we only consider the electric field vector. And you can imagine why that's a reasonable approximation in a lot of circumstances, certainly in non-magnetic materials, because the electric field vector is 3 times 10 to the 8 times as big as the magnetic field vector. So this is, it may be a simple geometry, but this result is always true for any electromagnetic wave. But now, we've analysed this from the side view. So what we were doing there was looking sideways on at the situation. I now want to look down the top view. So in other words, if I can find my view graph, which I used about a minute ago, here we go. There we go. I now want to analyse the situation looking, so I've done the side view, and the side view I've analysed by Faraday's law, and it's given me E over B is equal to the velocity. I now look down this way, the top view, and now I see electric field lines going down into the plane. I see electric field going down into the plane, and I see magnetic field lines going across my vision. I'm looking down this way, the electric field is going into the plane and the magnetic field is going across. So if we analyse that top view, the electric field lines are now down into the plane, and the magnetic, and this time it's the magnetic field lines which are going across my vision. And I can now analyse this, again remember we're in free space, as the Ampere-Maxwell law dynamic term. I can do the same sort of calculation for throwing a Stokes loop around the wavefront, but now as I go round this loop I'm looking at electric field lines through the loop. I'm looking, if you like, at, and I have a changing electric flux as the wavefront goes through. But as I go around my Stokes loop, I'm picking up the magnetic field. And again, you can see absolutely straightforward argument. In this leg, well, the magnetic field, remember, is now in the positive Z direction. All the magnetic field lines are going this way. In this leg, B dot ds is obviously naught because these are perpendicular. In this leg, they're parallel, and so my integral just becomes B, and B is constant, times L, where L is this width of the loop. I go around this leg, I get nothing, and I go around this leg, where the wave hasn't reached, so there's no magnetic field has arrived here yet, I get nothing. So the left-hand side of this equation is B times L. So, but now on the right-hand side, I have, of course, I've got my constant mu naught epsilon naught out front. Thank you very much. Didn't forget it on the view graph. And it's exactly the same argument. Just like we got BLV from the side view, we now get ELV from the top view, because it's the electric field lines which are coming through, and the electric field is now expanding into this region. And because of this, now my E times L times X d by dt becomes d x by dt EL, which is ELV. So the right-hand side of the Ampere-Maxwell law applied to this Stokes loop flown around the wavefront gives me that, again, the L's cancel off, gives me that B is equal to mu naught epsilon naught EV. Must be so. But this gives me a second criterion on the ratio of the electric field to the magnetic field. It gives, if I take the ratio of E over B now, I get 1 over mu naught epsilon naught V. And yeah, as I say, I'll make proper board notes on this. So from this one, this was figure 50, this was the Ampere-Maxwell law. I necessarily have this result here, that E over B is 1 over mu naught epsilon naught V. When I analyse from the Faraday point of view, the side view, I got E over B is equal to V, but this is the same wave propagating out from this shaking of the charged sheet. And so the E over B is the same wave, so therefore V is equal to 1 over mu naught epsilon naught V. And obviously then V squared is 1 over mu naught epsilon naught, and the velocity of propagation of the waves is 1 over mu naught epsilon naught. So what happens is if I shake a sheet of charge and I just throw a Stokes, for any velocity less than infinite, if I throw a Stokes loop around the wavefront in these two different senses, I get two different criteria for E over B, and they necessarily give me, of course it would be crackers if they didn't, they give me the result I got from what, if you like, is the pure mathsy analysis, where we take the curl of the curl and let that equal to minus del squared applied to the wavefront. So this is the, I wanted to do the derivation in two completely different ways because, it's the major thing. And indeed, we will be using, throughout our optics, and you probably knew this coming into the course, but it's very different to understand where it all came from than if somebody just tells you, oh, an electromagnetic wave, yeah, the electric field does this, and the magnetic field does that, sorry, in this geometry, magnetic field this way, electric field that way, direction of propagation. And when I say we'll come to all of the, we'll revisit this important calculation in the next lecture. But now I want to consider, again, rather qualitatively, what we've considered is this situation, where, and I hope you're convinced that if I had an infinite sheet of charge and I give it a kick upwards, it will send an electromagnetic wave down the room at precisely this geometry and this velocity. But what if then I stop the board, and it's plenty of friction in VO45, it stops, and now I give it a kick downwards at a quite definite time, capital T, later. I give it a whack downwards, and now it sends out a wave which is exactly opposite. Because the board's been kicked downwards, the magnetic field now goes this way. It's still propagating out here. This is still the YZ plane. And because it's got symmetry in the YZ plane, and it's infinite, the wave must go straight down the room. But now the magnetic field points to the right, and the electric field points upwards. So at a finite time t later, I give the board away, and after I have done that, the source is totally restored to its original condition. It started here, I gave it a whack upwards, I give it a whack downwards at a time capital T later, and it sends out, if you like, an equal and opposite wave. But the second wave doesn't catch up with the first one. Of course, they're both travelling at the speed of light. So if you, at a certain time capital T later hit the board the other way, you get a second wave, but and it doesn't matter whether it's the B field or the E field. If the B field was to the left from this wave, it's to the right from this one. If the E field was vertically downwards, as we considered the geometry from the top view, then it's vertically upwards here. But of course, this one doesn't catch up with this one. Yeah. This second wave has come out at a time t later. So in this region, up to here, we've still got superposition of fields. These are dynamic fields, but the Maxwell equations are linear, so the solutions always superpose. And because the solutions superpose, the two fields cancel out in this region, but they can never cancel out in this further region, because both waves are travelling at the same speed, and there's a delay. I've kicked this blackboard down at a time capital T later. And so I've totally restored the source to its original state. Let's say these boards are dead level. I kick it up a finite amount, wave comes out, wait a bit. It's already, kind of halfway down the... Well, of course, if it was a light wave, it would have passed us all by pretty quickly. But let's say now it's kind of halfway down the lecture theatre. I kick the board back down, and that sends out a wave. And by the time it's got halfway down the lecture theatre, the first wave has got to the back, and so on. So this is now the major new effect, the single major new effect of the Maxwell equations, is long after you've ceased any activity at the source, and the source has been restored entirely to its original condition. This little bundle of electric and magnetic fields continues just forever and ever and ever, unless it gets absorbed somewhere, for example, by our retina, and we see things with it. Now, as I've mentioned, we can't treat quantum electrodynamics yet, but we call this little bundle of electric and magnetic fields a photon. We can't explain why it comes in chunks, why it's quantized, why we get these E equals HF chunks. H, Planck's constant, won't come into our lectures at all. But you can understand that if I shake a charge upwards and then shake it downwards, it's going to send electromagnetic waves out from the source. So, we've still got a couple of minutes, and again, this is something that I'd like to, we've climbed K2. Now, it's been, an amazing sort of climb, because it gets us, sorry, this will be a little bit, distorted. Sometimes it's nice just to stop and admire the view, like, the course is very relentless, lectures, problem classes, and so on. This is taken from Feynman's 18th lecture, which I've, as usual, shamelessly cribbed for this lecture. And you can summarise the whole of classical physics in one table. And you'll see the whole of classical physics, so almost everything that was known. There's statistical averaging, you'll do statistical mechanics and thermodynamics next year, but the essential electromagnetism and mechanics is now, you can summarise in this one table. There's Maxwell's first equation, there's the second equation, there's the third equation, and now we can even understand why you can rewrite this equation in this way. When we were deriving it, it was natural because we started off with mu naught J plus mu naught epsilon naught dE by dt. That's the way it seemed very natural to do it. But it's obvious now, let's divide this equation through by mu naught epsilon naught, gives me a mu naught dividing through by mu naught epsilon naught. Well, dividing through by mu naught epsilon naught is the same as multiplying by c squared. So, and you cannot understate how, sort of overstate, sorry, how important that moment was. Is that the normal way is to eliminate, to make the redundant constant the permeability of free space. It's no longer an independent fundamental constant. So we usually write now the fourth equation as c squared del cross B is J over mu naught plus dE by dt. We don't even have conservation of charge as a separate law because it's built into the fourth Maxwell equation. We saw that this term is the one that ensures that charge is always conserved. So even that goes into brackets. It's not independent. We've still got to have a force law. We've still got to relate the force on moving charges. And I'm not going to do much on that in this course. Again, you did that with Kieran, you know, like if you have a charge and it's moving in an electric and magnetic field. Of course, it just accelerates uniformly in a pure electric field. And we know that the magnetic force is V cross B. Incidentally, we'll come back to the relativity of electric and magnetic fields. It might have occurred to you, having done some special rail last year, what's that V? Which Lorentz frame is it in? And we'll come, that's an important question. Somebody said to me, I saw a YouTube thing where somebody was saying magnetism is just an electrical effect in a moving coordinate system. There's some truth in that, but it's not just an effect. There is no coordinates, no Lorentz frame at all in which you can transform away the magnetic field of an electromagnetic wave. You can't, you know, that's, the electromagnetic wave cannot be broken down in that way. For slow-moving systems, magnetism is indeed a purely relativistic effect of electricity. Law of motion, you've still got to have Newton's laws. Well, this is just forces mass times acceleration. Newton's law with Einstein's modification, well, again, later in the course, and in fact, I'll come back to this a bit on Friday, this itself is also contained in the Maxwell equations. Again, just very kind of briefly, if I can find, no, I probably can't find it, so we'll leave that till tomorrow. The Lorentz, these equations are what's called Lorentz invariant, and Einstein used the Lorentz invariance to modify mechanics in this way. So in a sense, that even Einstein's work of 1905 is contained in the Maxwell equations. And then, of course, outside, and I've mentioned all along, gravitation is still, you know, as of February 2015, not unified with electromagnetism. So, yeah, enjoy the view and yeah, have a nice day. See you later.